Welcome to Principles of Flight, Section 5. In this section, we're going to look at the movement around the three axes. We'll revisit Newton's first law to look at manoeuvring and compare unaccelerated with accelerated flight. We'll then move on to look at the resolution of forces in turns and look at why the stalling speed increases as the bank increases in a turn. We have three axes that we use to describe the movement of a glider. The lateral axis moves from wingtip to wingtip and passes through the centre of gravity and is used to describe pitch. The longitudinal axis runs from nose to tail, again through the centre of gravity and at 90 degrees to the lateral axis. And this we use to describe the movement around it as roll. And we have the normal axis. This runs at 90 degrees to the other two axes and through the centre of gravity. And this is the axis we use to describe yaw. An important thing to note here is that the movements are irrespective of the attitude of the glider. So it doesn't matter if it's pointing down or up or whatever, the axes remain relative to the glider and not relative to the Earth. And this gives me a chance to just give you a little cautionary note. Very often you will see the normal axis described as the vertical axis. And the vertical axis technically isn't correct because the vertical axis would by definition be passing down to the Earth and down ultimately to the centre of the Earth. And so the normal axis would be a better descriptor. Pitch is about the lateral axis, as we can see here. The primary control for that is the elevator, and the lateral axis passes from basically wingtip to wingtip and through the centre of gravity. Roll is about the longitudinal axis passing from nose to tail and through the centre of gravity, and the primary control for this is the aileron. Yaw is about the normal axis, and the primary control for that is the rudder. So just summarising this, the movement is irrespective of the orientation with the Earth. So all of the axes are in relation to the glider, and the glider can move in around more than one axis at any one time. And that's something to remember as well. Now we can just take a look at steady speed and Newton's first law, just as a little reminder. And you can see the diagram on the right here. We have the two red lines, so total reaction acting vertically upwards and opposing weight. The total aerodynamic reaction has been divided into two vectors. One is called lift and the other drag, and lift is acting at 90 degrees to the flight path and drag is acting parallel with the flight path. When all of these forces are in equilibrium, the glider will be flying at a steady speed. If we want to change that situation, then we will need an extra force to be applied somewhere to the glider to change it. When we do that, we now call that accelerated flight. And there the forces are not in equilibrium. So if you look at this diagram, the glider on the right hand side is in unaccelerated flight, so the forces are all balanced and in equilibrium. In this example, the pilot's probably come back on the stick, increase the angle of attack, and the total reaction has increased in value. So now the glider will go up because the total reaction is greater than the weight, and that is accelerated flight. In steady flight in a sailplane, then, just as a little bit of food for thought, the pilot alters the speed by changing the angle of attack. This, of course, works for a sailplane and is one of the primary differences between a sailplane and a power plane. In this example here, we've got two gliders flying in steady flight. The one on the left at 60 knots, the one on the right at 100 knots. In both cases, the total reaction is equal to the weight. So the vertical total reaction equals the weight. But the glide slope is different. You can see on the left it's shallower than the one on the right. So at the higher speed, the glide slope is steeper. Also note that the lift component, almost parallel with the total reaction, is shorter than the total reaction. And the more steeply we dive, the shorter that lift component becomes and the greater the drag component becomes. So at lower speeds, lift is almost the same as total reaction in terms of value, and we can sometimes in calculations we might make that assumption and just say they're the same. At higher speeds, the lift reduces and the drag is increased. Now, if we want to transition from one of those states to the other, so let's say that we want to go from the steeper slope to the shallower one, then we will come back on the stick. And we're going to, in this case, we're going to transition from glide path 1 to glide path 2. The first thing that happens is we increase the angle of attack. Because we do that, the lift actually increases. The drag increases because we're maneuvering, moving a control, and the speed reduces. As the speed is reducing, the drag progressively decreases again until the drag is stabilized at a new value. What this means is as the angle of attack is increased, we generate more lift and the glider climbs, but we've also generate more drag, and so the glider decelerates and the drag progressively restabilizes to a new value. Once it's done that, the glider is now no longer in accelerated flight because the forces are back in equilibrium. Transitioning the other way, then, going from glide path 2 to glide path 1, the angle of attack is decreased. The wing generates less lift and the glider dives. As the speed increases, the drag increases. While this process is going on, again, this is termed accelerated flight. If you remember this graph, the coefficient of lift, something should start becoming apparent to you, and that is if we have a greater angle of attack, the lift is greater, but paradoxically, the speed is lower. If the angle of attack is small, then the lift is small, but the speed is high. And there's a sort of trade-off going in here. And we can see that from this simple formula. The total lift equals the coefficient of lift times half rho v squared s. And half rho is the air density, which we consider to be a constant. S is the area of the wing, and we consider that to be a constant. And that means that we've got two things that can vary: the coefficient of lift, or the angle of attack, and the velocity. And they trade off between each other. So at low speed, we have a large coefficient of lift and a small speed. And at high speed, we have a small coefficient of lift and a large effect from the velocity of the aircraft. So one trades off the other. If you increase one, you decrease the other. You increase the coefficient of lift, you decrease the velocity, and vice versa. Now, that's all very well. What we've looked at so far is what we call transient accelerated flight. So we change from one speed to another in these examples, and during that period, the aircraft is considered to be in accelerated flight. But we can also have a situation where the aircraft is in sustained accelerated flight, and that typically, for our purposes, will be the turn. And we can, the angle of attack needs to be increased at a constant airspeed in order to produce the extra lift required for the maneuver. So whenever we maneuver, we need extra lift. And we can get that either by increasing the angle of attack, or by increasing the speed, or indeed by doing both. When we look at the forces in a turn, you can see here on this diagram that the lift itself is acting at 90 degrees to the wing. That's okay if the wings are level, so lift equals weight. However, if the glider is banked, the vertical component of the lift is reduced. And lift is actually now acting in two directions. But the important thing here is the lift is no longer, the vertical component of lift no longer matches the vertical component of weight. We can resolve these two, when the glider is banked, the lift into two components, the horizontal and the vertical. The vertical component is clearly less than it was with the wings level, and the horizontal component acts in towards the turn, and it constitutes the turning force. We can adjust the amount of lift generated then to get the vertical component back to where it needs to be by either adjusting the speed or the angle of attack. The steeper the bank angles, or the tighter the turn, the greater the angle of attack required is to compensate for the loss in the vertical component of lift. And something to remember is we can increase the angle of attack to maintain the lift, but we can only go so far, because we already know that when the lift has reached its maximum value, the glider is at the stall. And therefore the glider is closer to the stall, and the stalling speed has increased in the turn, and we've got less room for maneuver, if you like. So when the wing is at its stalling angle, lift is its maximum, and if you want to get more lift, the only way of achieving that, once you're at that situation on the lift curve is to increase the speed. And what happens is the stall speed progressively increases as we're getting further banked, and this diagram shows it nicely. So when the wings are level, in our example, perhaps a K-13, the G forces are 1, so it's 1G, and the stalling speed perhaps 33 knots. If we bank the glider to 20 degrees of bank, we get a relatively small increase in G and 1.06, and the stalling speed goes up a small amount, not very much. If we bank to, let's say, 40 degrees of bank, the G has now gone up more significantly to 1.3, and the stalling speed is now 38 knots, so 5 knots greater than wings level. And if we increase the bank further to 60 degrees, which is really quite steep, of course, then it becomes about 2G, and the stalling speed will be 46 knots. So you can see quite a sharp increase in stalling speed as the bank increases, which is why your instructor in your practical flight training would have been getting you to fly at an appropriate speed to cater for this situation. Fine, so that's it. We've looked at the movement around the 3 axes of the glider, just looked again at Newton's first law and the fact that we need to introduce a force to maneuver. We've looked at the comparison between unaccelerated flight and accelerated flight, the resolution of forces in turns, and finally how the stalling speed increases in the turn. And I hope you found that helpful, and I will see you next time.